Okay, we're recording now. We've been talking about the heat dissipation, and we had discovered that when you produce X-rays, you also produce a lot of heat, an overwhelming amount of heat. 99% and more of all the energy available goes into heat, and only a very small fraction goes into actual X-ray production. And I backed up a few slides from where we had finished just to I'll give you a quick review of the heat dissipation mechanisms. We don't want to blow up our X-ray tubes, so we have to do something about it. And I'm just going to go quickly over some of the slides we had already covered just for a quick review. One of the things we can do is just heat up the tube warm up so that you don't start the day with a very cold target and impress a lot of heat all of a sudden in a small region of the target. And what would happen if you did was that sudden deposition of heat would produce expansion of the metal at that point, but that expansion would hit up against the cold metal sections of the target, and you would end up cracking the anode, blowing up the tube. So tube warm up. And to avoid that sudden point expansion at the anode. When you do impress a lot of heat at a particular point, another possibility is you drill a little hole. You may not completely explode the tube, but you drill a little hole in the target, which then releases oxygen. That oxygen attacks the filament, and pop goes the filament. Here's another mechanism that we had covered, the oil bath. We covered the X-ray tube entirely with oil, and the idea there is that oil has a high specific heat, meaning it'll absorb a lot of heat from the target without itself getting hot, so you maintain a good thermal differentiation between the target and the oil. And that oil completely bathes the X-ray tube and absorbs that radiated heat from the target. One of the very special things we do for the for a CT scanner is the CT scan, first of all, is the one modality that produces the greatest amount of heat. And that heat is, as we just said, one mechanism of absorbing that heat is with the oil. But that oil gets very hot, so that for CT scanning, what we do is we pump the oil out, being hot, pass it through a heat exchanger, cool it off, and then pump it back into the X-ray tube. So you're continuously moving cool oil into the tube to maintain that temperature differential between the target and the oil. Here is another mechanism. Just add a fan, blow air across the tube to keep that oil relatively cool. Actually, this picture comes from your own department. Then we have a choice of small and large focal spots. And a small focal spot has the advantage of heat capacity, or I should say disadvantage of heat capacity. If it's small focal spot, that means that the energy is concentrated over a very small region, and you are producing a lot of heat in a very small region, and we have a problem. That's the disadvantage. But we also have a huge advantage. Its spatial resolution is very good. When you produce X-rays from a very small region, a very small point, you get better spatial resolution. So we have a little a tug of war. You want to get the spatial resolution, but you don't want to blow up the tube. So you have to have a compromise between the two. And the compromise is you use it whenever you have very thin patients. And a large focal spot is just the opposite. It has the advantages of high heat capacity. How come? Because you're spreading out the energy over a large region of the target. And so no one little part of the region is getting the full heat. And so you have a greatly enhanced heat capacity. But now the disadvantages, you are spreading the energy over a relatively large focal spot size, and now your resolution is going to be degraded. And you would choose the larger focal spot sizes for the thicker patients. And here's a summary of the of those advantages and disadvantages. For small focal spots, great for spatial resolution, bad for heat capacity, and just the opposite. Large focal spots have great heat capacity, but relatively poor spatial resolution. Here's a common board question. I've heard about this question over and over again. And the question is, you desire to take a radiograph of a wrist. What focal spot size should you use? And why? Well, a wrist is relatively thin section. It's not going to take very large KBPs. It's not going to take very high MAs or exposure times. In other words, you don't produce very much heat. And if you don't produce very much heat, then you can afford to go to a small focal spot to capitalize on the enhanced image quality. Okay, so that question has been asked over and over again. It's a no-brainer. It's a giveaway question. Make sure you don't lose it. We showed you the actual mechanical, physical setup of these focal spots. Here you see a small focal spot and a large focal spot. And both of those focal spots are embedded in this a region of the cathode. Notice these side lobes over here. Those are your focusing cups. Those are the ones that grab or pinch the electrons such that they focus onto a small region of the focal spot. Down at the bottom of the slide, you see another very common board question. In mammography, what focal spot sizes do you use? And this is pretty universal. 0.1 millimeters for the small, 0.3 millimeters for the large. Think of that, 0.1 millimeters. You can hardly see 0.1 millimeters. And but that's the kind of small focal spots that we use. Why so small? Spatial resolution. And why can we get away with a small focal spot in mammography? Because you're not radiographing a hip. You're not radiographing an abdomen, very thick, very dense regions. In general, in mammography, you're imaging relatively small patient thicknesses compared to the standard radiographic type of thicknesses and densities that you have to deal with. In radiography, look at the sizes of the focal spots that we use there. 0.6 of a millimeter for the small, 1.2 for the large. That's pretty, that varies a little bit from manufacturer to manufacturer, but that's roughly the kinds of focal spot sizes we use in general radiography. Here's a further picture of the cathode assembly showing you the large focal spot and the small focal spot. And the arrangement is such that usually we use a rotating anode. There is your next heat dissipation mechanism, a rotating anode. And the idea of a rotating anode is that you have a target shown over here, and but that target is extended over the whole periphery of an anode disk. And what's happening is that the electrons from the filament fall at a particular area in space, a little area on the anode disk, but you get that disk to rotate, and as it rotates, you're spreading out the energy of the electrons over a much larger area, and there's a lot more metal to absorb the heat. Result, no one section of the target is going to get the full brunt of the heat that's being deposited. It's being spread out over the whole periphery of that anode disk. This is so significant that all of our modalities, from mammography to CT scanning, every one of them we use rotating anode. That's a standard feature of all our X-ray tubes. If you look on that image head on, this would be what it would look like. Remember, this is rotating, and this would be the region shown in red where the electrons are actually impacting on the target. But now, since you're rotating that anode target, you're spreading that energy out over that whole periphery. Again, bottom line, you get better heat capacity as a function of that. This is what it would look like, and you see the diameter or the disk. There's a certain angle involved, and this is the region down at the bottom where the electrons are actually impacting on the target. Right next to it, to the left of it, you see this little white. That looks like a damaged region where there's not a full-fledged crack, but the heat was such in that region that little holes were, or this whole little region was burnt into the target, and out comes oxygen. There's always oxygen in metals, and whenever you have you break the surface of that metal, now you have oxygen coming out, and it could be a minuscule amount of oxygen, but enough to oxidize the filament, and pop goes the filament. Here is the whole configuration in an X-ray tube. There's your cathode on the right, your filaments down here. On the left, you have your rotating anode, and you can see the angle that's involved there. And out comes the electrons, and off goes the X-rays. Okay. Now, we've been looking at the fact that these anodes are rotating. There's two parameters associated with the rotation. You have what is the disk diameter and what is the disk velocity. Let's look at the diameter first. What you see over here is a particular anode with a particular periphery track. But now let's look at a larger diameter anode. Do you see that? Per force, you're going to have a larger track. And if you have a larger track, that means that you can spread the energy of the electrons over a larger area, so that, again, the larger the diameter, the greater the heat capacity. There isn't as much energy deposited at any one point along that peripheral track. So that's going to be an important parameter for us. CT scanners, where you produce the greatest amount of heat, those tubes are significantly larger diameters to cash in on this particular feature. Typically, a standard general radiographic tube, you don't have to remember the numbers, but there would be between 3 inches and 4 inches in diameter, while a CT tube, you'll know a CT tube when you see it. It really looks like a huge, it's usually 5, 6, or 7 inch diameter anodes. Is that other parameter, the velocity. How fast is the velocity of that target? And the standard velocity is based on 60 cycles per second. That's your normal frequency coming in from the line. 60 cycles per second is 3,600 cycles per minute. And that you are going to have, every cycle corresponds to an RPM. So normally you would have 3,600 RPM, rotations per minute. And this is what we call the standard single phase. That's what you get right out of the line. And but there's always some slippage. So usually those are specified at 3,400 RPM instead of the full 3,600. Now there's another form of electrical generation, which we call three-phase. I'm going to be talking a little bit about that in subsequent slides, but we'll get back to that in full force in the next chapter. But in three-phase, you can triple up on that speed so that you would have 3 times 3,600. That's 10,800 RPM. But again, we have slippage, so that's specified at 10,000 RPM. When you go faster, you get better heat capacity. One of the advantages of three-phase is greatly enhanced heat capacity of the tubes. Then you have your the focal spots themselves on the anode are manufactured at different angles. We have one class of tubes that we call fixed angle anodes, and then we have biangular anodes. And the fixed angle, you have the small focal spot is just overlaid on the larger focal spot size. On the biangular, you have 2 separate tracks at 2 different angles. Let's take a look at each of those 2. Here is a fixed angle anode. You would have a large focal spot here, like we've just been talking about, and that would be spread out over the whole periphery of the anode. But then you would have the small focal spot focused in on a subsection of the large focal spot. That's what your fixed angle. In your biangular tubes, it would look like this, where you actually have two different angles and two different tracks, rather than one angle with a single track, which is what we just showed over here. So let's take a closer look at this. You can see the angle over here, one angle here, and then a steeper angle over here, and those correspond to two different sizes. You don't have to remember the numbers over here, but the idea that we can separate out into two tracks, having two different angles, and having two different capacities for image quality and heat capacity, like we've just been talking about. Then you have stationary anodes. We don't use stationary anodes in radiology, but I thought I'd show you what it looks like. And we usually use that in radiation oncology. Here's another mechanism of heat dissipation we don't particularly use. We used to use in radiology, people don't use them now, and that is just surround the target completely with copper, as you see in this image. The copper is an extremely good heat conductor, so that as you generate heat in the target, here's a target, it's circular over here, that heat energy is transferred to the copper and conducted away as a means by which you can keep the target relatively cool, so there won't be any meltdown or tube blow up. These types of target are relatively large angles to give you uniformity of the X-ray beam. One of the items we're going to be looking at a little bit later on is all of our diagnostic X-ray beams have some degree of non-uniformity, and that could be a problem. In therapy, you want to get a nice uniform dose over a whole tumor, so you have to have uniformity, and you go to these large angles. We have relatively small angles, and you can see the kinds of angles we have over here in this picture. We have relatively small angles, while this one over here is closer to 45 degrees. Well, moving on. This is, I think, where we left off last time, where we indicated another heat capacity mechanism is add carbon to your anode. Add carbon to the anode. What does the carbon do? The carbon, like the oil bath that we mentioned earlier, the carbon has a very high specific heat, meaning that it can get energy transferred to it from the anode disk to the carbon, but that serves like a heat sink. The carbon will not go up in temperature very much. That's what we mean by specific heat, and therefore you have a relatively good thermal differentiation between the two, which will enhance the conductivity of heat away from the anode to the carbon heat sink. This is what it actually looks like in an X-ray tube, and that's this dark area over here. It's bonded to the anode disk itself, and over here, if you take a look at this, this looks like a single angle region, and you can make out the track. With age, all of these tracks pit little bit by little bit, and that's what you see over here, and you can see that peripheral track all outlined. And again, you see the filaments down at the lower right-hand side, and the disc on the left. And again, where the electrons would impact on the disk, produce X-rays. Here's another heat dissipation mechanism, and that's the use of a molybdenum stem. A molybdenum stem around which the whole configuration rotates. That stem is made of molybdenum. Nothing to do with molybdenum in mammography tubes. We use molybdenum as a target material in mammography tubes, but here we use molybdenum as the stem, the shaft around which the anode will rotate. How come? What's the advantage of molybdenum? Molybdenum is a terrible heat conductor. We don't want heat from the anode to be, from the target disk, to be transferred back to the ball bearings. If you are going to have a configuration rotating, you need ball bearings. And ball bearings are very sensitive to heat. You do not want the heat to go back to the ball bearings and warp the ball bearings, with the result that then you'll have non-uniform rotation of the anode, so which will spoil the evenness of the energy distributed on the track. So this molybdenum stent prevents heat from being conducted back to the ball bearings. This is what that area looks like. Here's the ball bearings over here. You can't hardly see the shaft. It's back here connecting the disc to this region over here, around which this will rotate. Here's a better picture of that, showing you the ball bearings and the stem, the balloon stem, and the anode as we've just finished discussing. Okay, and this is the another picture of the actual X-ray tube showing you that that molybdenum shaft or stem. Here's another mechanism of heat dissipation. Pre-crack the anode. What you see in this slide, first of all, notice two different tracks, the large one and the small one. That indicates that this is a biangular anode. And but what's interesting over here is that you have these radial slits over here. Why radial slits? The idea is that if you impress a very high energy in a relatively small region, then with these radial slits that provide a space between each of these little sections, any one section over which the energy is deposited will expand. Any metal expands when you suddenly impress heat on it, but it'll expand into this expansion joint, if you like, this space in between these metal wedges. We have the same thing with railroad tracks. Railroad tracks, the tracks are separated with a little airspace so that the tracks on a hot day can expand into those regions, and you don't have one region buckling up against another region, which would spoil the railroad track, and in this case would lead to a cracking of the anode. So there's another mechanism of heat dissipation, provide for radial slits. Here's another view of another target. This one is a single angle target. You can see the pitted region. You can see the region of where the electrons actually hit, and then you see the radial slits just like before. Just another mechanism of heat dissipation. Here's some pictures of some damaged anodes. You have this pitting over here in the extreme left. You can see the crack over here. And likewise, if you look at the extreme right, you can see these this extreme damage to the anode, where there must have been a tremendous heat load impressed in a very short period of time, ruining the X-ray tube. But then you have various sources of damage. Here's another crack here in the middle. Here is probably the most interesting of all the mechanisms of heat capacity, and that's the one that's referred to on the basis of the line focus principle. The line focus principle. What we're going to be looking at is the role of the tube angle. The role of the tube angle. And where is the tube angle? It's the angle relative to the normal perpendicular line over here, and this is your angle of that particular one here. And we got to make some definitions. There's something called an actual size, and there's something called an effective size. The actual size is what this target actually measures, and while the effective size is the size as projected to the patient. Okay, the patient sees a size, while the actual size could be very much different than the size that's going to be looked at by the image receptor. That's going to be a very important idea for us. Actual size is going to control the heat capacity, while the effective size controls the image quality. Remember, we saw that small focal spots give you better image quality, and well, that size is going to depend on the angulation as projected to the image projector, to the image receptor rather. So let's see what that all means. Here is again a given actual size, a given effective size. What happens if we change the angle? Here is on the right where I have changed the angle. It's a smaller angle. In other words, it's steeper. It's steeper. And relative to the normal given up in the upper right-hand corner here, you can see that the angle here is going to be smaller than the angle over here. It's a steeper angulation. Well, so what? Well, let's take a look at that. If I kept the effective size the same, that's what I've done over here. Look what has happened to the actual size. It's so much greater. And if it's so much greater, you're going to have so much greater heat capacity. But yet, you have not suffered any penalty on the effective size. Remember, the effective size controls the image quality. But there's been no change in image quality. Why? Because there's no change in effective size. But yet, there's a very significant change in heat capacity. So here's an example where I've manipulated the angle to give me better heat capacity, but I don't pay any penalty. I don't have to give up on image quality. The image quality will be exactly the same. Okay, and that is one of the conclusions we get from the line focus principle. It's this: smaller angles give me better heat capacity without necessarily impacting image quality. No change in effective size or image quality the way I've just drawn it there. Let's take another view of that. Again, we start out with a given angle, and again we go to a different angle, but this time let's keep the actual size the same. Keeping the actual size the same means no change in heat capacity. But look at what's happened to the effective size. It's so much smaller than the larger angle. So here's another statement of the line focus principle. I can change the angle to make it smaller and now capitalize on image quality with no penalty on heat capacity. See, so going to a smaller angle will give me two possibilities: better image quality or better heat capacity. Okay, and in each case, I can maximize one without penalty on the other. How about this one? How about I go to a smaller angle, and here you see a greater actual size. Okay, over here we have what we had just finished, where now you have a better effective size, a smaller effective size. But what I want to show now is something in between. What if we go to the same smaller angle as before, but this time we'll cash in on both good things, both the heat capacity and the image quality. See, I'm not limited to just taking one extreme or the other extreme. I can take any combination of actual size, heat capacity, or effective size, image quality, any combination of the two. So according to this, it seems that I should be going to smaller and smaller angles. The smaller the angle, the better image quality, the better heat capacity. Well, there's a limit to how much I can push this, okay? But as seen in these slides, yes, you can cash in on both heat capacity and image quality. Okay? Those are both good. And those are the two statements so far of the line focus principle. But now, the bad. You can only push this so far because then heat effect kicks in. Heat effect is bad. I remember I mentioned earlier that all of our X-ray tubes in radiology have some non-uniformity. That non-uniformity is called the Heal effect. Okay? The Heal effect is going to give regions of the field that give you more intensity and regions of the field that will have less intensity. In other words, a non-uniform X-ray intensity from one end of the image to the other end of the image. We don't like that. And in practice, you've probably never noticed that. But as a physicist, I can measure it and show you that small difference from one end to the other end. It behooves us to keep that difference in intensity over the image to a point that it is not clinically visible, but it's there. And if you choose your parameters right, it'll kill you. And but in general, that Heal effect is bad. Let's take a look at what that Heal effect is all about. What is Heal effect? Here is a target with any particular angle. Here's a particular electron impacting on the target, producing your X-rays. There is in red the X-ray intensity pattern going out. That's cute. But now what happens when you go to a smaller angle, as we see here on the right? Follow again the electrons. Now, electrons are non-penetrating. In general, electrons, especially when they hit a solid object like an anode target, they don't penetrate very far. But they do penetrate certain molecular layers. And you can see both on the right and the left that the electrons have penetrated to the interior of the anode, whatever molecular layers it's capable of doing, but it will enter the target and produce the X-rays, not at the very surface of the target, but somewhere inside the target. But now notice what happens. Compare these two images. Back to the left. Notice that in the direction of the anode, the path length of the X-rays are greater than the path length in the direction of the cathode. You see that difference here? I've indicated in green the path length within the anode. Well, if the path lengths are different, that means that there'll be more attenuation of the X-rays along that path. The Heal effect is due to self-attenuation within the target. Self-attenuation within the target. And there'll always be a little bit more attenuation off toward the anode side than there is toward the cathode side. So that the emerging X-ray intensity is a little lower on the anode side. The anode side is also called the heel side, or the heel end of the tube. And there's your non-uniformity. One end of the tube is low X-ray intensity. The other end is high intensity. But now, when you go to a smaller angle, look at how much greater the path of the X-rays is within the target. It is so much greater, given by that green arrow. Compare the two green arrows. There is so much more attenuation within the tube, that within the target, that the intensity is greatly smaller. There's going to be a bigger difference between one end of the image and the other end of the image. It can get so bad that you have what's called the heel cutoff, where there'll be zero intensity off on that side of the image. Zero intensity, which means that there'll be a region in the image when you look at it that they'll be just completely cut off. So in a chest film, the top end of the chest film will be completely cut off. Okay. There is your Heal effect. There is the importance of it. You can either have a total cutoff, where you see nothing up there, or there could be intensity variations which can be confused with pathology. Either way, it is bad. Okay? There's your Heal cutoff there. You've never seen, I'm sure you've never seen Heal cutoff. We cannot tolerate Heal cutoff. When the engineer first installs an X-ray tube and takes his first test shot, if he sees Heal effect, he knows something's wrong. And he'll make sure that you never get to see it. He'll have to change tubes or do something about that Heal effect to prevent it. Okay? Here are some tube angles. Don't have to particularly remember the numbers, but now I'm listing things that we can do to minimize that Heal effect. We don't want to see it, so what can we do to make sure that we don't see it? Well, make sure you got the right tube, the right angle, because remember, Heal effect kills you at small angles. So if you see Heal effect, your tube has too small an angle. So make sure you got the right tube. Another mechanism is conform yourself to smaller field sizes, because the Heal effect appears greatest at the anode end. And so I'm going to show a picture of that. And your field size, if you do choose a smaller field size, cassette sizes, you sacrifice field coverage. You don't like this particular maneuver. That means that if you see a chest film, instead of a regular full field chest, you'd have to satisfy yourself with one image first and then go back to the patient and get another image and try to fuse the both, look at two images, and we don't do that, right? You do sacrifice field coverage. If you have a situation where you can get away with a smaller field size, fine. But in fluoroscopy, typically we can get away with smaller field sizes, right? When we acquire images through the fluoroscope, you're not looking at a 14 by 17 inch. Typical chest film will be a full 17 inches. So we don't like that particular maneuver to minimize heel effect, but you may have to do that, or you can increase the SID. That's the one they look for on the boards. If you see a heel effect, how can we minimize it or eliminate it? Change your SID. And here's a picture of what we're talking about. Here is an image plate, IP, set at a particular source image distance, the distance from this X-ray source, the tube focal spot, to where you're placing the image plate. And let's introduce the garbage over at the anode end. There's your corrupted beam, the edge that you have that cut off, that greatly decrease intensity. And one of the things, oops, let's go back to that. If you go to a smaller field size, you see that a smaller field size, since it doesn't extend out to the periphery where the heel effect is, you've eliminated the heel effect. But now you've sacrificed image size. Typically, we don't like that. Which is the preferred way of doing it? By going to a larger SID. So let's look at a larger SID. Again, we have the image plate at a particular SID. Again, the corrupted beam. Again, the presence of heel effect. But now let's move the image plate further away from the source. Look at that. Now, the peripheral edge of the image plate does not fall in the corrupted part of the beam. So you've missed the heel effect, and your mission is accomplished. Okay, that's how we usually handle this. If you have an X-ray tube that has that particular problem, it's the most practical way of minimizing this heel effect problem. What are the numbers in practice? The universal SID is 40 inches in radiography. 40 inches in radiography, and if I had a tube that had this problem, typically we solve that problem all the times that I've dealt with it is at 44 inches. Instead of 40, move out to 44. Those 4 inches are critical. When you look at an image, you see about, if you had the heel effect, about 2.5, 3 inches cut off at the top of the film if you had that heel cut off. That 4 inches further away of the SID disappears. You get a full field on your image. Okay, so there is your heel effect. We've got 3 statements. I'll refresh your memories on 3 statements. As the angle goes down, image quality goes up. Number 1. Number 2, as angle goes down, heat capacity goes up. And number 3, as angle goes down, heel effect goes up. And that's going to be the limitation to how small an angle you can use. Okay. Now, I've painted this heel effect as the bad guy, right? We don't want heel effect. We do anything we can to eliminate heel effect. But there's a very special condition in mammography where we love heel effect. We go out of our way to make sure that we have heel effect. Okay, because look at that statement. It assures the uniform exposure across the image plate. Didn't I just say that the heel effect actually produces a non-uniformity across the image plate? Over here, I'm saying we want the heel effect because it actually produces uniformity. There's a disconnect there. We got to describe what we mean by that. And the bottom of this slide is showing that two parameters that result from uniformity or non-uniformity. If you had an old-fashioned film mammography, if you have a non-uniform beam, what do you actually see in the image if you had a film? A non-uniform beam would mean over at the anode side, where there's very little radiation, very little density. You can't see anything because the film density would be so low. Over on the right-hand side, where there's lots of radiation intensity, there you will see your image. but one end of the image would be cut off, or very low intensity, or very low film density, very light, while the other one would have its full film density. That's if you're film density. Most of us live in a digital world where we do digital radiography or mammography, and there is no such thing, and I've mentioned this before, it's worth mentioning again. In the digital world, there's no such thing as an image that's too dark or too light. And you probably have realized that in CT scanning. If you're sitting by a CT scanner, have you ever had to scream at the tech, this image is just too black, I can't see anything on it? You've never seen such an image. Likewise, in ultrasound, you've never seen such an image. In nuclear medicine, you've never seen any such image, because the computer always makes sure that what you see has a neutral background density. There's no such thing as too black or too light. Or what happens in a digital modality when there's not enough radiation? It's not that it turns out too light. Not enough radiation means that you have a lot of noise, a lot of statistical variation, a lot of graininess on the image. That's what lack of radiation looks like in a digital image. It looks grainy, it looks noisy, it's noise. So let's go back to this idea of heel effect in mammography. We're going to use the heel effect to actually assure that the exposure is uniform. Why should we want to do that? To make sure that you have a uniform pattern of noise. You don't want one end of the mammogram with lots of noise where you can hardly see anything because there's so much variations in the intensity of the image as compared to the other side of the image. So just how does heel effect do this? Let's take a look at that. Here is a mammography setup where you have your X-ray beam incident on a breast, and there's your chest wall, and look at the problem we have. This is not the heel effect problem, this is just a geometric problem. At the chest wall, do you see that you miss a wedge of tissue there? Unacceptable. You don't want to miss part of that region of the breast at the chest wall. Well, that means that you can't use those kinds of beams in mammography. We don't use those kinds of beams in mammography. We use this kind of beam, a half beam geometry. There is your full beam. What we do is we place a hunk of lead in the beam and we cut out half the beam. So now with a half beam geometry, if we're going to knock out half the beam, the question is, which half are you going to throw away? Well, you would think immediately, hey, let's throw away the anode half because that's the one that has the garbage. Especially since in mammography, we usually tend to have very short SIDs. Remember what we said about SID? The shorter the SID, the more heel effect. The greater the SID, the less heel effect. In mammography, you are forced to go to shorter SIDs to get more radiation intensity, but that invites more heel effect. Okay? So and it invites more of this variation or loss of information at the chest wall. So block out part of the beam, and what half of the beam are we going to use? You would think we would use the good part, the one that doesn't have heel effect, but now we actually use the anode half. How come? Let's see why. Again, we have that situation. There's your half beam geometry. So, oops, what happened here? Let's go back to that one. There we go. You have your half beam geometry, so you solved the problem of the lost tissue wedge. But now, what happens and why should we use the anode half of the beam? Okay, follow this particular ray path, the one green dashed. Notice that the ray path through the breast, even for a compressed breast, this doesn't look very compressed the way I've drawn it, but even for a compressed or a breast, the tissue thickness is always thinner at the nipple end of the breast as compared to the chest wall. So what? Well, that means then that there'll be a lot more intensity at the, let me put it the other side, there'll be a lot less intensity at the chest wall than there is at the other end of the breast. Well, there's a non-uniformity of X-rays being transmitted to the image plate, giving you non-uniform noise, giving you a non-optimal image just because of the thickness of the breast. So now enter the heel effect. Remember that at the bottom of this slide, I'm just showing you what the problem is. If one end of the breast has high intensity, that means then that the noise will be very low. We're putting it the way I've drawn it here. At the chest wall, where your intensity is low, it'll be very noisy. So that'll obscure a lot of the pathology or the anatomy there. Okay, and so where intensity is low, the noise will be high. Where the intensity is high, the noise will be low. Notice noise always goes in the opposite direction of X-ray intensity. More photons, less noise. This is a non-uniform image, which we're trying to avoid. If it was a film modality, now instead of noise pattern, you see density patterns. One at the low intensity end, it'll be very light. At the high intensity, it'll be very black. Again, non-uniform images. But now enter the heel effect. Okay? The solution is the heel effect. When you use the anode end has a low intensity. That low intensity matches the low attenuation at that end of the beam. This is the way it would graphically look like. Okay, where here we go. The incident intensity is very low over here because of the heel effect, but that matches the fact that there's very little intensity. So you've equalized the amount of radiation that actually arrives at the image plate, and if you've equalized the intensity at the image plate, you've equalized the noise at the image plate. So that the noise pattern is very uniform from one end of the breast to the other end of the breast. Okay? Mission accomplished. You've canceled out the expected very a large variation of noise from one end of the image to the other end of the image by capitalizing on that one end of the X-ray pattern is very low intensity, the heel effect, which equalizes the very low attenuation within that area of the breast. Okay? All of our beams, number one, have half beam geometry, and all of our beams in mammography use the anode end to capitalize on the heel effect there. Okay. Now, I've painted the picture where you would just put a block of lead in the beam and to produce your half beam geometry. Actually, what we do is we have a combination of things. What you see in this image is I could, without placing any lead in the beam as one alternative, I can just angle the beam in such a manner that the edge of the beam comes right down along the chest wall. That'll solve my problem too. But toward the edges of any beam, there's always some variation, even if it's overall uniform. So we don't usually go all the way and angle the beam that much. What we do is a combination of a small angle plus the lead. It's a combination of both in practice. Okay? And if you look at any mammography machine, you'll see that the tube is slightly angled. Well, here's a summary of all the mechanisms of heat dissipation that we've talked about: the warm-up, the choice of focus spot, the oil bath around the tube housing. Just a second here. Time is almost up, but I'll hook up anyway, make sure that we don't get cut off. Okay, the air fan over the tube housing, the rotating anodes, the molybdenum stent, remember all of that, the slip disc, the carbon-backed anode is a summary of all the mechanisms that we've talked about. And now We talked about the line focus principle, abbreviated LFP, where we would go to a shallow angle target to capitalize on a more heat capacity. The last one leads us into the next chapter, and that's the use of three-phase electrical supply. Remember we mentioned earlier that with three-phase, you could have the velocity of the anode could be 3 times faster, and we indicated at that time that that would give us a better heat capacity. Okay, we'll be discussing that in the next chapter. But before we go to the next chapter, our time is almost up. But let's talk about heat rating and cooling charts. We've already established you don't want to blow up a tube. Well, how can you be assured that you won't blow it up? Every tube has a specifications on its heat capacity. It specifies what are your maximum exposure factors, what is the maximum KVP, what's the maximum MA, what's the maximum exposure times. And a typical rating chart looks like this. Let's take a look at this. First of all, look at the caption. This particular one is for 0.6 millimeter focal spot, 3,400 RPM. Right there, we know it's single phase because notice 3,400. Three phase would have given me 10,000. But this is single phase, 3,400 RPM. And notice that this is the small focal spots. Remember in general radiography, small was around 0.6. and large was around 1.2. And the actual graph itself, it plots out the KVP that you'd like to work at versus the exposure time in seconds along the x-axis. And then these various curves that you see within the graph represents the MA values. For instance, this one way at the bottom is 300 MA, and it goes up, I should say down, to 50 MA. Okay. Now, how do you use this? Okay. How do you use that? There's your focal spot size and rotor speed, and your KVP and exposure times, and your MA. How do you actually use this this graph? Okay. Let's look at the small focal spot, single phase, and use this example. And given 100 KVP, 150 MA, what's the maximum time that you can give? Okay. On this particular tube without blowing it up. Okay. Well, 100 KVP, identify where the 100 is, and then extend it out to where it intersects the 150 MA, and then just read out the time, 0.3 seconds. That's it. The maximum time that you could put on that tube for 100 kV and 150 MA is 0.3 of a second. Okay. Well, our time is up. I'll very quickly do this last one, small focal spots, but for three phase, just to prove a point, same parameters, 100 kV, 150 MA. Look at that. 5 seconds. 5 seconds. Remember we said that three phase allows for much greater heat capacity? This tube can take 5 seconds with three phase, and what was the result in the prior case? Here's a summary. The prior case was 0.3 seconds, but with three phase on that same small angle tube, small focal spot tube, 5 seconds. That's a huge difference. That'll allow a relatively thick patient to be exposed with a relatively small focal spot and enjoy better heat capacity. Well, let's wrap it up at that point. If are there any questions? Otherwise, I'll let you loose for the day. You all have a good day now.
Thanks, you too.
Have a good one.
Oh, God, I know.